Right now you see two waves up on the board, same two waves we saw yesterday. One's going one way, one's going the other way, or maybe they're both going in the same direction, but one's going faster than the other one. It doesn't really matter. We got two waves. We got a small wave, we got a big wave. One's a crest, one's a trough. We want to know what the pattern looks like when these two waves interfere with each other, when they come across each other and they form something that looks like neither of the two waves that you see, the combined wave. Well, we're going to use something called the superposition principle to figure that out. The superposition principle involves simply adding numbers together and occasionally subtracting numbers. In both cases, whether you're adding or subtracting, they're usually pretty simple numbers, so it's usually a pretty simple thing to do. So let's do this question. We got two waves here, but we got three sections really. The first section is where wave number one doesn't yet overlap with wave number two. We don't have to worry too much about what the pattern looks like there because there's nothing to interfere with. The first wave is going to be the pattern that we see until the point where it starts interfering with the second wave. Same thing happens after this whole thing is over as well. The third phase of it where the second wave isn't interfering with the first wave. So if we look at this area down here, the pattern that we see is simply the second bigger wave, the trough of the wave, because they're not interfering. They're not overlapping with each other, so they're not interfering. The interference happens in this middle section right here, where you've got a crest and a trough, or two different waves in the same place. Well, how do we figure out what the pattern looks like there? Well, as I said a minute ago, we're either going to add or subtract numbers. But what numbers are we going to add or subtract? Let's take a look at every vertical line, how far above or below each wave is. So, for instance, this first vertical line right here, where the two waves are interfering with each other, the first wave, the smaller wave, is above the x-axis there. How far above? How many blocks above is it? From here to here, it is 2. So we got a 2 up here. And how far is this one below? It's about 1, right? About. Okay, it might be a little bit more than 1, but it's pretty close. We don't have to be perfect on this. We just want to be close to it. We're going to say it's 1 below, but because it's 1 below, we're actually going to make it a negative 1. 2 plus negative 1 gives me what? Seth, what does 2 plus negative 1 give me? Yes. Good. Good. Sorry, positive 1. What did you say, Seth? Positive 1 or negative 1? I think you did too. It is 1 anyways. 2 plus negative 1 gives me 1, right? 2 minus 1 is 1. Next vertical line. This one is, how far is this one above? Both the same, right? How far is this one below? 2 above, 2 below. Seth. You got a 2, and we got a negative 2. They combine to give me what? Thank you, Seth. So our point that we draw is literally right on that axis there. 2 above, we got about 2.5 below. Those add up to give me negative 0.5, right? 2 plus negative 2.5 gives me negative 0.5. Okay, about 2 above, 3 below, 1 below. Okay, this one's going to be about here, about here. When we combine those, it's going to look something like this. So although when you are looking at this wave, if you're actually looking at this wave on a slinky or whatever, you're not going to see all these pretty colors, red, blue, and green. You are going to see the pattern that we see right there. Okay, when we look at it, we're not going to see this portion of that wave and this portion of that wave. What we're going to see is the blue portion, the green portion, of course, but we're going to see that red portion in the middle that is the combined blue wave and green wave. Stephanie had a question? It's always going to be linear? What do you mean? Oh, I see what you mean. I see what you mean. So is the middle part always going to be like this, or like this, or could it be like this? Yeah, it could be something like that. It would be unlikely that it would be something like that. You'd probably be dealing with, say, 3 or 4 waves combining to give you something like that, or 2 crazier waves than what we have right there. But it is possible to get something like that. Generally, you're probably going to expect to see something fairly smooth, though. Okay, not for sure, but usually you would. All right? You guys okay with that? You guys comfortable with that? There is, I believe, don't quote me on this, I'll check the test. I'll check the test before I actually give it to you. Remind me of that before Monday. But I believe there's a single question on the test that's exactly like this. Okay, piece of graph paper, you got a couple waves. All you got to do is add up the waves and get the resulting interference pattern, okay? That should be a nice 2 out of 2 or 3 out of 3, whatever that question's out of. Okay, it should be a nice, easy question for you. By the way, what kind of interference is this? Constructive or destructive interference? What kind is it? Destructive interference. How do you know it's destructive, Jacob, as opposed to constructive? A trough and a crest, yeah. And when you have a trough and a crest, it makes a, all right, a trough and a crest, it makes a smaller wave. When you make a smaller wave than what we started with, that's what we got here, right? Okay, we're taking away from the wave. Okay, it's destructive interference. Okay, when we're making a bigger wave, okay, 2 crests come together, 2 troughs come together, that's called constructive interference. All right? Good. All right, here's where we left off yesterday. We started, we had flipped the page and I said, no, we're not going to bother doing this today. Today we are going to do it. A new phenomenon called diffraction. Diffraction of waves is the spreading out of wave. If I open the door to my classroom and I talk loud, then people out in the hallway will hear me. And they don't have to be right outside the door. They can be down the hallway and they'll still hear me. That's because when my voice goes out the opening of that door, it spreads out around the door and goes down the hallway. When a water wave goes through an opening like this, that water wave goes through that opening and it spreads out like this. That's called diffraction. When a wave spreads out around something, we call it diffraction. See what I mean there? We're not changing direction. We're not bending the wave. The wave is still going in the same direction. The wave was going this way. The wave's still going this way. But now the wave is spreading out. It's not just this narrow little area right here that the opening was. It's spreading out around that opening. Now, the amount of diffraction, in other words, the amount of spreading out, sometimes we call it the angle of spread, right? That's a little bit of diffraction, a little bit of spreading out, a small angle of spread, versus this. A lot of diffraction, a lot of spreading out, a lot of angle of spread. Okay, the amount of diffraction, whether it's just a little bit, like we showed on the first diagram, or a lot, like we show right here, depends upon a couple of things. How much it spreads out depends upon the size of the opening. If I open that door and I talk loud, the diffraction of my voice, the diffraction of the sound waves going out that door will be more if the door is narrower. And it might be a little bit counterintuitive. You'd think, oh, more sound goes out if the door is wide, right? It does. More sound does go out if the door is wide. But it spreads out more if the door is narrow. It diffracts more if the door is narrow. So if the size of the opening is skinny or narrow, we get more diffraction. We'll say smaller opening, we get more diffraction. If you're anything like me, you have trouble remembering these things. Okay, when I can understand something, When I can go back to a basic concept and understand that concept, I don't have any trouble with it. I'm pretty good at that. But when I have to remember something like, oh, wait, size of the opening, bigger, smaller, more diffraction, less diffraction, things like that mess me up. So how do I remember this? How do I get this right every single time I'm teaching it? I always have a way. I always have to have a way of remembering it. You know, I remember this one. If you drop a pebble in water, a rock into water, what kind of waves does it make? Looks like circles, right? Whole circles, complete circles, right? Point source waves, we call them. Okay? Drop a pebble into water, drop a bunch of pebbles into water, or even just hit that water with your fingertip. Okay, hit it, hit it, hit it, hit it, hit it, and it makes these circular waves, complete circular waves. Well, the closer I get an opening that looks like this, then I got an opening that looks like this. The closer I get, the smaller the opening that I get, the closer that I'm getting to a single point source. Okay, the wave goes through here, it spreads out. But the wave goes through here. This is almost like just throwing a rock into the water. It's a really, really small source of the wave on this side. So if it's like the rock being thrown into the water, it's going to be closer to the complete circle. In other words, the smaller the opening, the closer it is to a rock. The smaller the opening, the more spreading out we get. The closer it is to a full circle of a wave, or the more diffraction we get. Okay, that's how I remember that one. In fact, that's the reason why we get more diffraction when we get a smaller opening, because it is closer to a single point source, like throwing a rock into the water. Smaller opening, more diffraction. Bigger opening, hey, bigger opening, more wave goes through, but it spreads out less. What's the other factor that affects diffraction? Well, it's the frequency of the wave. And frequency of the wave is, of course, related to the wavelength. So we could talk about the second factor as being wavelength just as easily as we could talk about it as being frequency. They have the opposite effect. If frequency does one thing to the amount of diffraction, then wavelength does the opposite, because, as we know, frequency and wavelength are inversely proportional to each other. So how does the frequency affect the amount of diffraction? Well, I have a tough time with this one as well. Tough time remembering this one as well. Anything that I have to remember, I have a tough time with. Okay, I have to understand it, or I have to have a way of remembering it. Let me tell you how I remember this one. Tell you, when I was in high school, and I learned this in grade 11, I, for the life of me, couldn't get it. The first year I was teaching here, 20 years ago, was the first time. I was 23 years old when I was teaching here for the first time. And I still couldn't remember, could never remember consistently how the frequency of the wave affected the amount of diffraction. And I had to teach this stuff. What am I going to do? I got to teach this stuff, and I can't remember it. Well, I got lucky one day, because one day I lived in an apartment just at the bottom of the hill in Okotoks, just below Okotoks Junior High School. You know where I'm talking about? It's that old brown building that's just at the bottom of the hill underneath Okotoks Junior High School. No, I know where you mean, but that's next to it. Okay. Bottom line is, here's my apartment down here. Here's the hill, and then Okotoks Junior High School is up here. I used to, when I would go to bed, I used to turn my clock radio on, set the alarm on my clock radio, and then I'd turn it to a station that I liked, and then I'd hit the sleep button. And then my radio would go for 59 minutes, and then it would shut off by itself after 59 minutes. That's how I'd fall asleep. I always like to be listening to something when I fall asleep. Still, to this day, I put my earbuds on and listen to podcasts on my iPhone to this day to fall asleep. But at that time, I just turned my clock radio on, would have it shut off by itself after 59 minutes, and I'd be asleep, so it would all be good. I used to listen to this one particular show on the radio. And then one night, I go to turn it on, and that show's not there. It's not on the radio station anymore. So I'm searching around the radio to find this radio, the show. Has it moved to a new station? Can't find it. Can't find it. Can't find it. Well, what am I going to do? I can't fall asleep now. Well, it was a week later. I was driving home from school. School was way over here. Driving home from school. And I'm flipping the radio station around, and it's 11 o'clock at night. It's time to go to bed. And I hear my radio show, and it's on this other station. So I hear it. I go back to my apartment, and I tune in the dial on my clock radio. Can't get the radio show. I can get it in my car way over here when I'm leaving school, but I can't get it on my clock radio in my apartment at the bottom of the hill. Well, when I first listened to that radio show, back before it switched stations, it was on AM radio. AM radio is called amplitude modulation. That's what AM stands for. Okay, AM radio is low frequency. If you ever look at a radio dial, it'll be measured in KHZ, kilohertz, thousands of hertz. Okay, that's a high frequency, thousands of hertz. But when I heard it the second time, when I discovered where it was in my car, it was on FM radio, frequency modulation. You don't need to remember what AM and FM stand for. Bottom line is frequency modulation. FM is a higher frequency. It's, if you ever look at your radio, it's megahertz, millions of hertz. So this is kilohertz, or thousands of hertz, and this is megahertz, billions of hertz. Well, I'm listening to here's the radio waves. I'm listening to my radio show on AM radio before they go and switch stations on me. And this is what's happening. The radio waves are coming from over here somewhere top of the hill. They go over the edge of the hill, but they diffract. They spread out. And what happens when they spread out? Well, the radio in my apartment detects those radio waves, and I can hear my radio show. Right? I can hear it when it's AM radio, when it's low frequency radio waves. But when they switch to FM, watch what happens when they switch to FM radio. Okay, FM is higher frequency. Those waves are closer together than the AM. They come from the top of the hill. They still spread out when they go over the edge of the hill. But FM radio waves, higher frequency radio waves, diffract less. They spread out, they diffract, but they don't diffract as much. So what happens? Well, when I'm driving home from school, my car still detects those radio waves. I hear my radio show. But when I'm in my apartment, what happens? They just go right over top of my roof. So AM radio, which is low frequency, must diffract more than FM radio, which is high frequency. If we go back to the page of notes here, the frequency of the wave, we're going to say lower frequency, more diffraction. I could hear AM in my apartment. I couldn't hear FM in my apartment because AM, which is kilohertz, diffracts more over the edge of the hill than FM, which is megahertz. To this day, almost 20 years later, that's how I remember that. That's how I remember that small frequencies diffract more than big frequencies. So, go back to our door here again. Okay? If I yell out this door, and I want people to hear me, okay, the wider the door, the more sound is going to go out the door. The narrower the door, the more it's going to spread out down the hallway. But if I yell with a higher frequency, like maybe it's not me yelling, maybe it's a female teacher yelling with a higher frequency voice, or a higher pitch voice, their voice will diffract more. It's not necessarily going to be louder. You're not necessarily going to get more sound going out the door, but you're going to get it spreading out more and down the hallway better because it's a higher frequency sound than mine is. Does that make sense? sorry, no, sorry, it's the other way around, right? Other way around, sorry. The lower frequency is going to diffract more. So my voice will diffract more and spread out. Again, not necessarily louder than the higher frequency one. Not necessarily more sound going out. But the lower frequency, my voice, is going to spread out more and go down the hallway better. Yep, yep. Now, wavelength is inversely related to frequency. So this one's easy. Frequency, low frequency gives me more diffraction than high wavelength gives me more diffraction. It's going to have the exact opposite effect as frequency. Until my first year teaching here, I could never remember these two. But after I had my little issue with AM/FM radio in my apartment, I could always remember this one. And as long as I remembered this one, then the third one just kind of fell into place because I knew that wavelength was inversely related to frequency. You've got a handout in front of you right now that looks like this. This is diffraction, but this time we have two openings instead of just one. So I'm showing here probably more diffraction than would actually happen. It's exaggerated, but you still get the point, right? You get the first opening here, right here. You get waves going through it, and it spreads out. It spreads out like this. The second wave goes through this opening, again, spreads out as a circular wave like this. It diffracts through both openings. Now, the point that I want to make with this diagram is I want you to see how diffraction that we just took a look at a few minutes ago and interference that we reviewed about 20 minutes ago and then did yesterday, how they relate to each other. When I've got diffraction taking place through two openings, and I've got two diffracted waves being produced here, then those two waves will at certain points pass by one another. In other words, they'll interfere with each other. Now, this gets a little bit cumbersome here, but if you follow along, it shouldn't be too bad here. When a crest meets a crest, in other words, from a crest from wave 1 meets a crest from wave 2, then we get constructive interference. When a trough meets a trough, we get constructive interference. When a crest meets a trough, we get destructive interference. We want to see what the wave interference pattern looks like as a result of these two diffracted waves interfering with each other. Let's label a couple of things first. On your paper, as well as on my paper, you should be able to see every second line is a little bit heavier than the first line. Can you see that? So this one right here is heavier than this one. This one is heavier than this one. This one is heavier than this one. Heavy, light, and so on. Can you see that? The heavy lines, we're going to call them crests. And then the lighter lines, we're going to call them troughs. So we got a crest, we got a trough, we got a crest, we got a trough, a crest and a trough, and so on and so on and so on. Now, we've got that from both of these waves. We've got two series of crests and two series of troughs. I want to put a little red dot. Now, wherever we have constructive interference. In other words, wherever we have crest and crest or trough and trough meeting each other. I want to put a little red dot. You may, if you have two different colors of pens, you know, red and blue or green and pink, you may choose to use different colors. It doesn't matter. Okay, it doesn't matter. If you don't have two different colors, that's fine too. Use X's and O's instead of red and blue. It doesn't matter, but make it two different patterns here, okay? My constructive interference, crest and crest, trough and trough, is going to be a red dot. Yours might be an X, it might be a green dot, doesn't really matter. Let's take a look now at where we get constructive interference. In other words, where heavy line meets heavy line, crest meets crest, or light line meets light line. In other words, trough and trough. Doesn't matter where we start. Okay, let's take a look at this area right here in the middle. Heavy, heavy, light, light, heavy, heavy, light, light, heavy, heavy, light, light, Okay, there's constructive interference. There's more spots though. If we go over here, it's trough, trough, crest, crest, trough, trough, crest, crest, trough, trough, crest, crest. Again, constructive interference. Go over here a little bit, same deal. Everywhere where you see crest and crest or trough and trough, then I want you to put a little red dot or whatever your color of dot is, or your pattern X or dot or whatever. Same thing on the other side. Everywhere where you see heavy lines meeting each other or light lines meeting each other, I want you to put your dot. There's a lot of dots there. Right now, it looks like pretty much a random pattern of dots. But I'm also going to draw in a bunch of green dots, which are going to represent destructive interference. Destructive interference is going to occur when a crest meets a trough. In other words, when a heavy line meets a light line, a skinny line. Well, here's a crest and a trough. Here's a crest and a trough. Again, we're going to fill in all these intersection points where crests meet troughs. It's going to look something like this. Now what we're going to do is, we got kindergartners at the school now. Let's do a little kindergarten work. Join the dots. All the green dots, let's join them. All the red dots, let's join them. So what we end up seeing here is these lines. If you look at this from above, okay, let's say it's two water waves that are going through these two openings, both diffracting and interfering. What we end up seeing is, from above, are these lines of constructive and destructive interference. So everywhere on these red lines, you got big waves. You got either big crests or big troughs, constructive interference. Everywhere on the green lines, you've got little waves or even no wave, destructive interference, where the waves have canceled each other out. Let's say this is a swimming pool, and you've got, for whatever reason, some big source of waves right here at source number 1, some big source of waves at source number 2 here. You're lying on an air mattress in this swimming pool, reading a book, trying to read a book at least. If you're lying on one of these green lines, you're going to be sitting there enjoying the sun, reading your book, no problem, because it's going to be calm water. There's destructive interference wherever you see a green line. But if you move over just a little bit on your air mattress in the water to where one of the red lines are, what's going to happen? It's not going to be a very comfortable read because you're going to be bobbing up and down like crazy. Because there's bigger crests that are twice as big as the originals, troughs that are twice as big as the originals. You're going to have these massive crests and troughs, these massive waves as a result of constructive interference. So destructive interference lines, sometimes we call them nodal lines, where we have destructive interference, and constructive interference, sometimes we call them antinodal lines. Now, this doesn't just work with water waves. Water waves you can visualize, right? You can picture a guy or a girl on an air mattress trying to read a book in the swimming pool, and you can picture these big waves air mattress bobbing up and down, or no waves. The air mattress is just on calm water. You can see that, right, in your mind. You can visualize it. But this can also happen with other types of waves as well, like sound. If you do this right, you get two constant sounds. It doesn't work so much with speakers and stereos because the music that you're playing on the speakers and stereos is changing frequency, right? So the diffraction you get doesn't look like this. It's not as neat as this. We'd have to have a constant frequency. But if you take two sound speakers and generate the same constant frequency from both of those speakers, speaker 1 and speaker 2, then you will get these areas of really loud sound and then no sound, and then loud sound and then no sound. If you were to set up those two speakers with the exact same frequency and you were to walk across right here, you would hear loud sound, quiet, loud sound, quiet, loud sound, quiet. Again, corresponding to the constructive interference lines or antinodal lines in destructive interference nodal lines. Make sense? Kind of, at least?